Let's do a quick review of heating curves and heat capacity, heat of vaporization, heat of fusion, and all of that. So here's a heating curve, and on a heating curve it then has temperature in this direction increasing and the amount of heat energy that you're adding. So this is a linear amount of heat energy. So you'd start here. This would be, with this water, this would be the solid form of ice. This plateau right here then represents the amount of heat energy for taking ice to liquid water. The water then increases in temperature, and this plateau represents the heat energy required for turning the liquid into steam. This would be the heat of vaporization, and then this has been heating up the steam in the heat curve like that. So a couple of things. One is you recall that we talked about the different types of molecular motion, and so in a solid we have mainly vibrational motion. In the liquid we have then so this would be the liquid. We have vibrational, rotational, and a little bit of translational in the liquid. And finally, in the gas, we have vibrational, rotational, and a lot of translational. And that's directly related to the temperature. A couple of things, other things on this heating curve. This amount of energy right here would represent the heat of fusion, be the heat required to melt ice or released when ice melts. Okay, and this plateau then is the heat of vaporization. And this represents the heat energy then that's required to take liquid water to the gas state. And so all of this is dependent then on, in the case of water, the intermolecular forces. And so you have then the polar aspects of water, and you end up then making a dipole-dipole hydrogen bond. And so in the solid, they're pretty tightly together. They just have a little bit of vibrational energy. As you add heat energy, you break some of the hydrogen bonds in the act of melting, and that's this heat of fusion. And now you have increased molecular motion that increases until you get to the gas, where you separate and break all of these hydrogen bonds, and you have individual water molecules. And that's going to take quite a bit of energy, and so the heat of vaporization is larger because the amount of energy is larger right here. So let's look really fast at a couple of other things that you see on these heating curves. One is the molar heat capacity. The other one is the specific heat capacity. And so the molar heat capacity is then the amount of heat energy that the material captures, and that's the amount of heat energy in joules. Sometimes it's in calories, so it's a measurement of the heat energy. And the molar heat energy would be to take 1 mole of material and increase it by 1 degree C. When you use these calculations, the units then are telling you what to do, and so it's important to understand that. So that's the molar heat capacity. Specific heat is also heat capacity. It just now has the amount of heat energy that it takes for a mass amount instead of a mole amount of material to raise it 1 degree C. So that's a quick overview of all of those things. Hopefully that's helpful.